you don't know me, my name is Daniel Sanky, and today I'm going to talk about artificial intelligence in song recognition. So let me tell you a little bit about myself before we go on. So I'm from Valley Stream, New York. Another way, if some of you don't know where that is, another easy way to think about it is I am 10 to 15 minutes away from JFK Airport. I attended Cornell University from 2016 to 2020, majoring in information science with a concentration in data science and minors in business, psychology, and music. During my time at Cornell, I was able to be able to continue exploring my interest while also exploring information science. From there, I did my master's at Weill Cornell Graduate School of Medicine in biostatistics and data science from 2020 to 2021. Currently, aside from being an instructor here at Inspirit AI, I'm an associate data scientist at IQVIA. And aside from coding, I cook, swim, and yes, I play Minecraft. Has this ever happened to you? So say if you're in like some sort of, like if you're in a restaurant or if you're in a store and you hear a song that you really like, and you really want to know what that song is. You try to think like, okay, are there things that I can think of, like how the song goes, the chorus? But unfortunately, during the time between when you hear the song and when you get home and you are able to search it up, you forget it. Well, the good news is, in today's society, or at least since the early, and by today I mean since the early 2000s, companies have developed technology that is capable of recognizing songs through listening to auditory data. One example of this I actually had was one night I was watching the Kelly Clarkson show for some reason, and I heard this song by a cover by her band called All Around the World by Lisa Stansfield, but her band was performing it, and I really liked the groove of it. So this presentation will be interactive. I should let that warning be done in advance. So let me ask you a question. So when you try to recognize a song, what things do you think about? You can either say it or you can type it in the chat. Tempo, tune, the chorus, tune, lyrics, acoustics, yep. Lyrics, yep. The tone, yes, all of these are good possibilities. So I'm going to actually show a couple of videos during this. That's floating meeting controls. What's that? And so the first one is about how the human mind might think about music. A lot of these do have timestamps, so I might cut it a little bit shorter than intended. So the first one is from the Tonight Show with Jimmy Fallon. And he's playing against Taylor Swift. I know, right? Good timing to use this.
We're going to start playing a song
because of
one
the
instrument at a time. Taylor and I can buzz in and guess as soon as we know the song. But if you guess wrong, the other person gets a chance to steal.
Oh, treacherous.
You can play.
Crazy.
You can play along at home. Roots, let's hear the first song whenever you're ready. Oh, man.
Yeah, so this is how the show works. So the Roots, like they go instrument by instrument playing the song, and whoever buzzes in first and guesses it right gets a point. So let's go to the first timestamp here.
Love it if you get. Let's hear the next song.
And if you can guess the songs, feel free to type it in the chat.
Love it if you guess it now. Bad Guy, Billie Eilish. All right, coming back, man.
So in this case, Jimmy Fallon was able to recognize the first song as Bad Guy by Billie Eilish because of the bass line, bass and synthesizer. And let's go to the next song in this video.
I know.
All right, let's hear the next song.
Okay. Is it No Scrubs?
How do you get that?
chords in a song.
Gosh. The chords in the song. All right, yeah.
I'm really too excited. I feel I'm flushed and.
I know me. I know.
So in this case, Taylor Swift was able to guess the song No Scrubs because of the chord progression, because of the chords. So the next clip we have is, next couple of clips are actually about how certain apps are able to, how we have technology that is now capable of recognizing songs beyond what the human mind can do. So I'm actually going to go a little bit out of order, and let's start with Shazam. So some of you might know Shazam was actually one of the first song recognition apps. I believe it came out, so it was originally released to the public in like the early 2000s. And I believe in 2007, it was acquired by Apple. Let's talk about Shazam.
You know when you don't know what song is playing and it's driving you crazy? With the Shazam app from the App Store, you just hold up your iPhone to the song. And in seconds, you'll know who sings it and where to get it. That's the iPhone, solving life's dilemmas, one app at a time.
That's the second app about Shazam. We'll talk a little bit more about that in the next slide. And the last one is Google's version of Shazam.
Come on.
What's that song?
So that was the other one. There was when Google introduced the Google search function. I think that was around actually 2021. So let's go a little bit deeper into how this works. So imagine you're at the store and you hear a song you like. How it used to be is like you open the app, or how it is you open the app and you tap the button. Some people have tapped the Shazam, others have search by song. And from there, the device records audio. Given the audio, a digital fingerprint is created, and within seconds, matches it to its database of millions of songs. That sounds very generic. We will talk a little bit, we'll go deeper into the concept of a digital fingerprint. Lastly, the app gives you the track name and other information, including composer, where to find it, and lyrics. So in this case, the example here of an output is Wake Me Up by Avicii, and I show you, you can open it in Spotify, Apple Music, something called Deezer. I don't really know what that is. So throughout the course of this program, we kind of discussed three different types of data: numerical data, text, and image. And based on our lectures with NLP and convolutional neural networks, we know that an important step is to convert these data into numbers so that our algorithms can better process the data. So does anyone have any ideas as to how sound can be converted into numerical data? Pitch and maybe volume, frequency, using the amplitude and frequency. Sound waves as a matrix, since those are metrical. Fourier transform, okay. All good responses, folks. Let's talk about a little bit of physics for a moment. So as you might know, sound travels through waves that are created by object vibrations. We can distinguish different pitches by looking at the frequency, or the number of times a wave occurs in a period of time. So a low pitch would have a lower frequency, seen here, whereas a high pitch would have a higher frequency, and thus a lower wavelength. So how do we distinguish this with regards to frequency? This picture here shows the frequency in hertz, the range of frequency in hertz, and how different instruments can be categorized within these ranges. So we can see that a pipe organ and synthesizers have a very wide range of frequencies. In contrast to the trumpet, which can only go from, where is this? 164.81 hertz, or roughly E, to, where is this? Somewhere between 987 and 1046. This is an interesting visualization to show how different instruments have different ranges of frequency. So after we convert the sound into numeric data with frequencies, we can actually plot the changes in frequency with respect to time in a visualization called a spectrogram. For some of you who may have done, I think my group is actually doing the music recommenders. I believe we briefly discussed about this during the last class. So in this plot, we have time on the x-axis and frequency on the y. And then our z here, which is represented by color, is the amplitude or the volume, which is recorded in decibels. So in this case, the lighter the color, the louder it is, or the much more it stands out. Right. But translating a spectrogram like this into data that a computer can understand can require a lot of data, too much data to realistically scale upwards, because we have so much information that is being entered and being recorded. So we do have a need to find a way to simplify this, which is why we have this concept called audio fingerprints. So this is a rather simplified version called a well, the way that audio fingerprint is created is that the spectrogram here is converted into something that we like to call a constellation map, where the strongest peaks, which are indicated by the lightest color in the spectrogram, are chosen and represented by points, which would allow us to create a scatter plot, aka this constellation map. So we have time on the x-axis, frequency on the y, and there's no third dimension. We just have the points which stand out the most being represented by x's within the plot. So how exactly do we use these audio fingerprints? For that, I'm actually going to outsource to YouTube to explain. So let's go to our little first timestamp. And I know we're a little bit short on time, so I am going to be fast forwarding a little bit.
In the song, or perhaps every point in Shazam's massive music archive. This obviously is going to take a lot of computation time. This is not how Shazam looks for a match. First, Shazam categorizes fingerprints in a clever way. We don't search to see if a note exists in a song. We search to see if several notes exist separated by a particular time, just as our brain does. This becomes our searchable address for a hash table. Hashes and hash functions are an incredibly useful technique that appear everywhere in computer science. Hash functions can be found in search algorithms used by Google to make sure files are downloaded correctly and are the backbone of cryptocurrencies like Bitcoin. A hash function takes a varying length of input and produces a fixed length output called a hash. In practice, the input can be anything from a short piece of text like a password to a long data stream like an entire movie.
And I'll send that link in the chat. Let's go to the next timestamp here.
Titles. The word "the" being stored on the same shelf. Now imagine, instead of book titles, our hash function takes data from our two frequencies separated by a particular time as an input, t, and produces a number between 1 and say 1 billion. First, we go through our database of songs and calculate the hash number for each anchor point part. Songs will contain multiple anchor points, which will allow us to categorize short snippets of songs by the frequency of the anchor point, the frequency of the following point, and the time between them. And just like the library, we store each anchor point in order by the hash. These addresses are also categorized with song IDs and timestamps within the song in a secondary hash table, allowing us to search for matching songs. This makes it much faster to locate our matches, and to find our song, we require multiple matching anchor points. This ingenious method of song recognition allowed Shazam to be sold for $400 million to Apple and help you figure out just what that catchy song is. This is a very simplified view of how the programming of...
Yep, so that is the next part. So in here we mentioned about how, sorry, I just lost my train of thought here. So here we kind of talk about how we use these audio fingerprints to help us look into the song. For the sake of time, I did send a link to the video to everyone so that you may look at it in your own free time. And now that we kind of understand a little bit more about how songs are produced, like how we use computers to actually help us recognize songs, let's think about a couple of questions here. So could you imagine any other applications to song recognition, or at least the technology that is used for song recognition? And if you do know, feel free to type in the chat. Voice recognition, could you apply it to other forms of audio? Yeah, speech typing, yep. Possibly even emotion detection, if you think about it. Because certain tones can lead to perceiving different emotions. And the last part is, could you imagine any this last question, I kind of want to break into 2 different points. The first one is, can you imagine any points where the technology we use for voice recognition can potentially return incorrect results? Voices can change, people can get sick. Yep. I kind of say the difference between a live recording versus a reel. Like, I believe one good example was Frozen, actually. So I believe Idina Menzel sang Let It Go. Let's see, when did that song come out? Frozen came out in, I'm always going to forget this. Okay, Frozen came out in 2013. I forget when, but a few years later, Idina Menzel sang during the New Year's Rockin' Eve. I believe that was like 2014, 2015-ish. And during that, she kind of sounded really different. So it's like kind of like the power of changing audio, like using technology to change the human voice. Yep, people can sample songs. Some artists or some songs can sound similar. Yes, this can be especially true for, I believe there's a concept called the 4-chord song, where every hit band uses the same 4 chords in every single song. Yep, it can interpret a generic sound effect, exactly. And could you imagine any ethical concerns about the technology we have for song recognition? Yep, it can record someone's voice. Sometimes we don't want our technology to be listening to our conversations. Deepfakes. Exactly. So the last part here is a couple of things I'll send in the chat for your own interest. I believe Garrison mentioned before that the technology behind Shazam, here's a quote. Shazam started out in 2002, but the original paper, which the system is actually based off, came out in 2003. And here's a paper by a professor at Columbia University, which explains how Shazam worked at the time of publishing. Second one is a fun game show called Beat Shazam, which actually tests how fast can humans recognize songs. I think they have 5 seasons out right now. Yeah, and the show is hosted by Jamie Foxx. And then the last one is how to create a music recognition program using Python.